Recording in progress.
Okay, welcome to Robotics 1. In today's class, I'm going to talk about some important aspects, essentially the forward kinematics, coordinate frames, vectors, and application of three-dimensional kinematics to robotics. So in today's class, I'm going to talk about So this is lesson 1, and I will upload these notes onto Canvas. Okay. Forward kinematics. So what is forward kinematics? Forward kinematics is given joint angles find position of end effector. So let me discuss what this means. Imagine you have a simple robot arm, and that robot arm looks something like this. You have a motor, you have a robot arm, and here is some type of a gripper, a fixed shape gripper. This length is fixed, and here, as I discussed, there is a motor. So this is the motor. So forward kinematics means given this angle theta, find the position of the end effector. So the position of end effector. And if I say the position of the end effector, since it's a two-dimensional system, that you have only two axes, one is x and one is y. I want to find out p x comma y. And some of you may say, hey, this is way too simple. Yes, it is simple. So this distance, the horizontal distance along x is going to be L cosine theta. Vertical distance along y is going to be L sine theta. And here we use the short form for cosine theta as c theta and for sine theta as s theta. So the forward kinematics problem for this is given value of theta, what is p of x, and the answer to that is L cosine theta, and what is p of y, which is L sine theta. Now what I want to do is I want to add the concept of unit vectors to it. So what is a unit vector? Unit vector is an indication of direction. Unit vector I is one unit in x direction, and j means one unit in y direction. So I can define my position px comma y. I can define this as a position vector, and this is very important. I can define this as a position vector from the origin O. So I'm going to show this position vector here. This is my position vector, and every vector has the magnitude and direction that is given as L cosine theta I plus L sine theta g. Are you with me so far? Now, the robots, typically, they have two types of joints. One is a rotary joint and other one is the prismatic joint. So the rotary joint is shown something like this. And rotary joint is nothing but a hinge. So if I were to draw the three-dimensional representation of the figure, then I can say that my robot arm is something like this. So this is the three-dimensional representation of the robot arm that is shown over here, where you have this motor over here, and this is my point P. Everybody understood this? But since the Z direction, this is the Z direction or the Z elevation, since this distance is constant, I really don't have to worry about it because it's just that direction, that dimension is going to remain constant. So as the joint changes, only Px and Py would change. Everyone understood this? So what is a vector? Vector needs direction and magnitude. What is the unit vector? Unit vector is only indicative of direction. Its magnitude is 1. Unit vector is actually tells you in what direction you have to orient. So this unit vector x is telling me is if I say 1i or if I just say I, which means look horizontal. If I just say j, that means look vertical. And when I have a combination of I and j, it tells me to get to that destination, I need to travel L cosine theta units in x direction or L cosine theta I, and then I have to travel L sine theta units in the j direction. Everyone understood this? Alternatively, I can go first in j direction and still go in x direction. I will still reach the same destination. Everyone understood this? Understood this? Are you sure? Yes. Now comes the tricky part. So imagine what I have, and this is the most important part. Imagine that I have this coordinate x0, y0, okay, and I'm going to denote the unit vector I0 and unit. Let me not add unit vectors right now. This is x0 and y0. This is the coordinate frame. Now I'm going to rotate this coordinate frame by angle theta. I'm going to rotate this coordinate frame by angle theta. So what's going to happen? This is super important. Probably you studied this earlier somewhere, but wait till I explain you what that means. So this is rotated by y1, and this angle is theta. Now, one super important thing is we are going to use the right hand coordinate system. So what do I mean by right hand coordinate system? Right hand coordinate systems, and I need to stand here so that the online students can see. Right hand, then these are the three vectors. So basically curl last two fingers, you have x, y, and z. Now, how do you decide the coordinates? Now, I want you to look at the board. This is x, this is y, and z coming out of the board. This is super important. Because believe it or not, when we talk about the 3D kinematics, this coordinate frame could be somewhere in different orientation. And at that time, if you don't follow the right-hand coordinate frame, the answers would be wrong. So remember, every time, right hand, always think about it. Then thumb is always going to be X, Y, and Z is coming out. If you have coordinate frame where X is flipped, and then in this triad, X is this, Y is this, Z is going in. Everyone understood this? If your coordinate frame is like this, X, Y, Z. Coordinate frame like this, X, Y, Z. Everyone understood this? Do not forget the right-hand coordinate frame. Everywhere you will use right-hand coordinate frame. So along with the right-hand coordinate frame, we have to be very careful about rotations because the directions of rotation are super important. So now the answer to that is something like this. So everyone agrees that this is my X, this is my Y, and this is my Z. What is positive rotation? Curl your fingers in the direction of rotation. And if your thumb is pointing towards the positive axis, whether it is positive X, positive Y, or positive Z, then that rotation is positive. What it means is, check this out. If I have the rotation something like this, curl my fingers, right hand fingers, around the rotation in the same direction as the rotation. Thumb is pointing towards positive Z. Do you agree with me? Which means this rotation is positive. If X is like this, curl your fingers in the direction of rotation. Can you see my thumb is opposite to X, which means this is a negative rotation. Are you with me so far? So this is negative. Curl your fingers, and I'm going to show it something like this. Here, curl your fingers in the direction of the rotation. Thumb is pointing toward positive Y, which means that rotation is positive. So what I want you to do is, this is my X naught, this is my Y naught. So do we agree that my Z naught is coming over here? And this rotation that I have shown is the rotation about Z naught. So this rotation is positive. Okay. Now what I want to do is, I want to solve this tricky problem of coordinate transformation. And I want you to look at the things that I'm going to do very carefully, because that is entire chapter 2, coordinate transformation. So now I have two axes. I have X naught, X1. I have Y naught, Y1. So what I'm going to do is, I'm going to create a matrix. Okay, I'm going to create a matrix. On the top, I'm going to say projection of. Projection of. And here, I'm going to say projection on. Now, I would tell you why that is important. So basically, along the columns, it will be the projection of, and along the rows, it will be projection on. So this is always the new coordinate system. This is always the old coordinate system. So what I'm going to do is, I'm going to write down the new coordinate system. What is my new coordinate system? My initial coordinate system was X naught, Y naught, and Z naught. You agree with me? My new coordinate system is X1, Y1, and believe it or not, Z1. Z1. Because and Z naught and Z1, they are one and the same. So I'm going to write down projection of X1, Y1, Z1 on X naught, Y naught, and Z naught. Do you agree with me? So let's solve the easy part. Do you agree with me? Projection of Z1, this is super important, and I want you to pay attention. Projection of Z1 on Z0 is what? 1. Because Z1 does not have any component on X0 or Y0. You agree? Z1 is only aligned with Z0. No X0, no Y0. So Z1 is only aligned with X0, X0, Y0. Do you agree with me? Now, let's apply the same logic to X1. So, if you look at X1, I would draw a vertical line. As soon as I drop the vertical line, I know the components of X1 to go from this point to this point. This is the tricky part. So online students may not see this, but if I want to go from this point to this point, I need to travel in this direction, which is going to be, look at the diagram that I have drawn, it is going to be, so if this distance for the time being is 1, just imagine if this distance for the time being is 1, it would be L cosine theta, which is 1 cosine theta. So do you agree with me that the projection of X1 on X0 is cosine theta, because L is 1. Okay. So then I get to this point. From here, I have to go up. And if I have to go up, you agree with me, I have to travel L sine theta. L is 1. So cosine theta, sine theta. The most important part is I would be traveling in the same direction as X0, which means this is positive cosine theta. I will be traveling in the same direction as Y0, which means positive sine theta. So what that means is, I'm going to show the arrows here. This is going to be cosine theta. This is going to be sine theta, which means here comes the punchline. Projection of X1 on X0 is going to be cosine theta, Y0 will be sine theta. If I call this rotation theta Z, because this is the rotation about Z0 and Z1, so projection of theta Z, I would say this will be theta Z, theta Z. What is the projection of X1 on Z0? 0. Are you with me so far? We'll leave it like that. Now, next thing what I want to do is, I want to look at, and this is the most important part, projection of Y0, projection of Y1 on Y0. So draw a horizontal line. And now, here comes the tricky part. So I have to go something like this. Now, what that means, and so I want you to observe. First, I will have to go Y0, the projection of Y1. Projection of Y1 on Y0 is again cosine theta, but in the positive direction. But the projection of Y1 on X0 is minus sine theta. Are you okay? Once again. So this is Y1. This is theta. So the vertical distance, vertical projection here is cosine theta, but it's positive. Why it is positive? Because you are going in the same direction as Y0. On the other hand, if you look at this projection, that is sine theta. But this sine theta projection is opposite of X0, so that's negative. Everyone understood this? Okay, so this becomes, first, I will say Y1 projection on Y0 is cosine theta Z minus sine theta Are you with me so far? And then clearly we said earlier, here it will be 0, here it will be 0. Are you with me so far? This is the only projection matrix that you have to remember. I can derive the same projection matrix about x naught, rotation about x naught, rotation about y naught. But the most important projection matrix that we will use throughout entire robotics one is this. Nothing else. So I will explain this once again. Projection matrix is like projection of the new coordinate frame onto the old coordinate frame. So the projection of, projection on, new is here. X1, Y1, Z1 is the new rotated coordinate frame. X0, Y0, Z0 is the old coordinate frame. Always, when you want to find out the projection, what do? You draw a vertical line and find out sine and cosine component, exactly what we did over here. So if I find out the sine and cosine component of x1, I see it is cosine theta z on x naught and sine theta z on y naught. Similarly, when I look at y1, I see on y1, I have negative sine theta z on x naught and positive cosine theta z on y naught. And that is the projection matrix. How does it translate to unit vectors? Now, what I'm going to do is, I'm going to assign the unit vectors. And if you have taken robotics before, or if you have done coordinate transformation before, probably you have seen this transformation. So I'm going to say I naught is the unit vector around x naught. A naught is the unit vector around y naught. Then I'm going to say I1 and I'm going to say G1. So I will assign the same coordinate systems here. I naught, G naught, E naught. Again, I will assign the same thing. I1, A1, E1. So, and how do we do it? I naught is equal to cosine theta to I1 plus, sorry, minus sine theta z G1 plus 0 K1. Then J naught is equal to sine theta z I1 plus cosine theta z J1 plus 0 K1. And K naught is equal to 0 I1 plus 0 K1 plus 1 K1. Everyone understood this? This is nothing but the transformation that will take us from one coordinate frame to the other coordinate frame. Now, one thing I want you to notice that since the rotation is about Z naught, we get 1 at the diagonal. And then respective columns and rows will get zeros. So can you see that I have a 0 here, I have a 0 here, I have a 0 here, and I have a 0 here. Are you with me so far? So just for my own satisfaction, and we are not going to use this ever again, but for my own satisfaction, I would actually derive the transformations when you have the rotations about the different coordinates. But we are not going to use it. This is the cosine theta minus sine theta, cosine theta. That is the only transformation that you should remember. All the problems in robotics 1 will use this transformation, nothing else. Kinematics, dynamics, inverse kinematics, inverse dynamics. This is the transformation that you should remember. But just for the sake of completion and finishing chapter 2, let me add the other transformation. So imagine what I have is I have x naught, y naught, z naught. And we take the rotation about x naught. So this is going to be theta x. And when I do the rotation about, so this is going to look a little bit weird because now this will be in this frame. So this is going to look like this. Again, curl your fingers in the direction of rotation. Is this rotation positive or negative? Positive. One thing I want to tell you that for some reason, if this rotation instead of being positive is negative, which means x1 is going down, y1 is going on in the first coordinate, what you will do is you will just change the sign of theta. And please understand, if you change the sign of theta, cosine of minus theta is cosine theta, but sine of minus theta is minus sine theta. Means this sign would flip. Are you with me so far? Any questions? So now here, what's going to happen? Again, draw the projection. Again, drawing projections. What is our new frame? Y1 and Z1. What is our old frame? X0, Y0, and Z0. So we have to draw perpendiculars onto the old frame. So we have to draw the perpendiculars on the old frame. And then I would write the same thing again. X0, Y0, Z0. We have this big matrix x1, y1, z1. Let's start with the easy part. Can you see the projection of x1 on x0 is 1? Are you with me so far? As soon as we get 1, all other columns and rows become 0. So we just had to find out 4 elements. So let's look at y1. Projection of y1 on y0. Let's look at the easy part. So this is theta x. This is theta x. Since I've drawn this in 3D, it might look a bit difficult, but it's actually not difficult at all. If you see, this is cosine theta x. Do you agree with me? And you are going in this direction. And this guy is sine theta. Now, one thing that I want you to observe, that this cosine theta x is in the same direction as y0. Do you agree with me? Sine theta x is in the same direction as z0. Do you agree with me? So which means I will write cosine theta x, sine theta x. Do you agree with me? Now what I want to do is, I want to look at this part. So this is going to be like this, and this is going to be like this. Now please understand, if I take this projection this is going to be cosine theta x, and if I take this projection, this is going to be sine theta x. So if you look at the cosine theta x is in the same direction as z naught. Cosine theta x is the same direction, so this becomes cosine theta x. But if you look at the projection of z1 onto y1, this is going to be minus sine theta x. And this, I'll give you a minute to think about it. It's kind of, I didn't draw a good projection. So this projection ideally, how does it make sense? It should look like. So can you see that sine theta is parallel to y naught, but it's in the opposite direction of y naught? Everyone understood this? Now the last coordinate transformation, and just to be fair, we are not going to use this transformation, but I want you to understand that same technique can be used for rotation about anything. So the next transformation is going to be the rotation about y naught. So the rotation about y naught. And then I would do the root. This is my y naught, x naught, v naught, and the rotation about y naught is theta y, and which means my y1 is going to be like this, and then the rotation be like this. Are you with me so far? Then clearly we have to repeat the same process and draw the projections. Let me see. I will draw this. Since this is three-dimensional, so I have this, I have this. And if I draw the projection here, this would actually look like. So this is the projection here. So what I will do is I will write down the cosine theta y, sine theta y, then cosine theta y and sine theta y. And I would just go ahead and write down x naught, y naught, z naught. One, y1, z1. And then as you see, y0 and y1 are aligned. So I will write 1 over here, 0, 0, 0, 0. Projection of x1, projection of x1. So this is my x1. This is my z1. So projection of x1 onto x0 is sine, no, x1 on x0. x1 on x0 is cosine theta y. So this is cosine theta y, right? Are you with me? Projection of x1 on z0 is minus sine theta y. Are you with me? Because see here. Here, it will go like this. And basically, as you can see, my V1 is going in the opposite direction. So I will draw it properly. Let me draw this properly. So since it's a three-dimensional figure, it is difficult to visualize. And then for Z1 is sine theta y and then cosine theta y. So what you have is you have now if you want to write this in a matrix form, what that means is you have these unit vectors I naught, J naught, I naught, K naught, K naught is equal to, you have this matrix multiplied by I1, J1 and K1. And I don't know if you remember matrix multiplication. First row, first column. So first row, first column is going to give me something like this. I naught. So this is the first row. Multiply that with the first column. That is going to give me cosine theta y I1 plus 0 K1 plus sine theta y K1. Are you with me? Then if you do J naught is equal to 0 I1 1 G1 plus 0 K1. Are you with me? And K naught is equal to minus sine theta y I1 plus 0 J1 plus cosine theta y. Everyone understood this? Now this matrix has some special properties. This is called as the rotation matrix. And this rotation matrix is called as an orthonormal matrix. Why is this called an orthonormal matrix? So this is called as orthonormal matrix because the determinant of this matrix is 1. So it is very easy to find out the determinant here. 1 multiplied by minus cosine theta, cosine square theta minus of minus sine square theta, which means determinant of this matrix, which is called as the rotation matrix, is equal to 1. You agree with me? And each row or each column is perpendicular to each other. The reason, what does this mean by orthonormal? Ortho, so normal means perpendicular. So each row or each column is perpendicular to each other. That means if you take the dot product of any vector, either a column vector or a row vector, with any other column vector or row vector, you are going to get 0. Everyone understood this? So what do I mean by taking the dot product? Dot product is nothing but multiplying the elements, like a vector multiplication. So if you take the dot product of any row vector or a column vector with any other row vector or column vector, you are going to get 0. Dot product 0 means what? A multiplied by A dot B cosine theta is equal to 0, which means theta is equal to 90 degrees. Are you with me? Now, what is the geometric interpretation for this? Geometric interpretation for this is, if you think about it, no matter how much you travel in the x direction or whatever vector you have in I direction, there is no j component to it, which means, to give you an understanding of this, projection of x axis onto y axis is 0. There is no projection, right? You have x axis and you have y axis. Unless your vector is somewhere in between, there is no projection. So which means x does not have any projection on y. Y does not have any projection on x. Same thing with z. Z does not have any projection on x. Z does not have projection on y, which means all these three axes form a triad, which means they are independent. You cannot resolve them in terms of each other. That's why they are normal. And why they are orthonormal? Because all the vectors are unit vectors. Everyone understood this? That is the reason why this matrix is an orthonormal matrix. What is the most important property of an orthonormal matrix? The most important property of orthonormal matrix is inverse is equal to transpose. So R inverse is equal to R transpose. What does that mean? That means, now let me give an example. Imagine I have a vector. So I have a vector like x0, y0, z0. And I have a rotation matrix. Okay. And this rotation matrix is x1, y1, z1. Do you agree with me? This is exactly what we have. We have x0, y0, j0 here, z0 here, x1, which is I1, j1, and k1 over here, right? Which means what I have done is I have expressed x0. I have expressed x0 as the components of I1, j1, k1, j0 as the component of I1, j1, k1, k0 as the component of I1, j1, k1. Now I want to flip it. So what I want to do is I want to take this R matrix on this side. So what would I have to do is I have to pre-multiply by R inverse. Do you agree with me? So I need to multiply here by R inverse. I have to multiply here by R inverse. So if I multiply by R inverse on both sides, what I get is I get R inverse. I need to draw x naught, y naught, v naught is equal to R inverse multiplied by R. That gives me an identity matrix I. And I have x1, y1, v1. Finding inverse is very painful, but since the matrix is orthonormal, inverse is equal to transpose. So I can just write R transpose x0, y0, z0 is equal to x1, y1, z1. So that means I can write x1, y1, z1 is equal to R transpose x0, y0, z0, which means I can replace x1 by I1, j1, k1, I0, j0, k0. Everyone understood this? So rotation matrices are super duper important. And once you understand the rotation matrices, forward kinematics is piece of cake. So I'm going to stop here, and in this week, what I want you to do is I want you to review all MATLAB videos. And it is super important because I'm gonna work out forward kinematics problem. And initially, I will work the first couple of problems, I'll work out by hand. And then I will just use MATLAB to solve forward kinematics problem because it's way too simpler, easier. And if you have a very complicated robot, you are not going to use hand calculations. You are going to use MATLAB, or you are going to use Gazebo or VREP or some other software. So with that, I'm going to stop here. So what I want to do is, I want to give you a quick tour of Technology Center, show you what robotics lab we have, show you what 3D printing equipment that we have, and we have access to a lot of these free resources. So I'm going to stop here and I will upload the slides by a couple of days. Any questions from my online students? If there are no questions, I will see you next Monday.